Robert is a well-known computer scientist. He, together with your friend, invented boosting. Boosting, as many of you know, is a machine learning algorithm that creates a highly accurate predictor by combining many weak signals and inaccurate rules of thumb. Boosting algorithms have been successfully applied in biology, vision, and speech recognition, and apparently some hedge funds have also successfully used it. Robert and his co-author received multiple awards for this invention, including the Gödel Prize. And Robert is a principal researcher at Microsoft. Before that, he was a professor of computer science at Princeton University for more than 10 years. And before that, he worked at the AT&T Bell Labs for more than 10 years. He is a member of the National Academy of Engineering and the National Academy of Sciences. His main research interest is in machine learning, and today we are privileged to learn about Robert's latest research in this area. Please help me welcome Robert Schapire.
Okay, thank you very much for inviting me and for that introduction. Talked a lot about boosting, which I'm not going to talk about, but I am going to talk about more recent research on something called the contextual bandits problem that I'll be describing, which is really about the problem of how to learn to make decisions that will give high reward. Very basic problem. So to introduce this, let me start with a concrete example, and this is just meant as an example. I'm not going to be talking about websites and so on through the entire talk. It's just meant to make things concrete. So websites today very often need to make these very quick decisions as to what content to present to a user, like which advertisements, which news articles to present, and so on. So there's kind of this repeated process that takes place in a website. So what happens first is that the website is visited by a user, and generally the user shows up with some information. In other words, the website knows something about this person, like the person's profile, maybe some demographic information, the browsing history, and so on. And based on that information, the website makes a decision, decides on which advertisement to present or which news article to present, and so on. And then the user responds in some way, like the person clicks on the article, doesn't click on it, never comes back, and so on. And the goal, of course, is to make choices that will elicit some kind of desired behavior in this person. Like usually you want the person to click on the advertisements or the article as much as possible. Okay, so that's one example. Here's another example. Again, these are meant to kind of generate intuition of the kind of problem we're looking at. So this is the problem of medical treatment and kind of a cartoonish version of that. So what happens in medical treatment is a doctor gets visited by a patient, and the patient shows up, and the patient has symptoms and family history and their test results and so on. And based on all that information, the doctor makes a decision, decides on a treatment, prescribes a drug, tells the person to go get rest, and so on. So makes a decision, decides on a treatment, and then the patient responds in some way. So maybe the person gets better, maybe he gets worse, maybe he never comes back, and so on. And again, the goal is to make decisions that will maximize favorable outcomes. You want the patient to get better as much as is possible. Okay, so both of these, they clearly have similarities, and abstracting a bit, they're both examples of what's called in the machine learning community the contextual bandits problem, which is kind of an obscure name. But it's really just describing this process. So more abstractly, there's an agent of some kind that needs to make decisions. In this talk, I'll be calling that agent the learner. And what happens repeatedly is that the learner is presented with some information that we call context. So this might be a description of the web user in the first example. Then the learner decides on an action. So for instance, decides which article to present to the person. And then the learner gets to observe some reward, like the person clicks, maybe that's a reward of 1. If the person doesn't click, it's a reward of 0. And importantly, the learner only gets to observe the reward for the action that was actually taken. Just as happens in real life, you make a decision, you only find out what happens for the action you took, not what would have happened for the other actions. And it's that aspect of where you only get to see the reward for the action that was taken that makes it what's called a bandit problem. The name comes up for historical reasons. And the goal is to learn to choose to make actions that will maximize reward over the long term. Okay? And it's called the contextual bandits problem because there's context. So that's where the name comes from. So I hope you can see that this is really a very general and fundamental problem. It's the problem of how to learn to make intelligent decisions that will maximize reward over the long term. How to learn to make good decisions through experience. Okay, so maybe this is a good point in the talk for me to make a confession. For the sake of full disclosure, the confession is that I know very little about finance. I can sort of manage to choose mutual funds for my 401k. It's about what I know about finance, so I hope you'll forgive me. I warned the organizers and they said, well, come anyway. And so I didn't give any examples based on finance because I figured they would just seem naive, or they actually would have been naive, not seem naive. But you know, from what little I know about investing in finance, it seems like this is relevant, or at least related, that you're making a series of decisions over time based on what you know at that moment, based on context, and you're trying to figure out how to make those decisions to maximize reward. Every time you make a decision, you get a reward, which is whatever your investment goes up or down, and you're trying to maximize that over the long term. Okay? Okay, so good. So what are the issues? What are some of the issues that come up in thinking about how to solve this problem? So the first issue is a very classic dilemma, which is that on the one hand, we're trying to take what we've already learned and take advantage of it, make decisions based on what we think will be the best action. You want to give the patient the drug that you think is the best drug for that patient, of course. That's called exploitation. You're trying to exploit what you already know. But at the same time, you have to be trying new stuff. There might be entirely different ways of prescribing drugs or different drugs yet to be invented and so on that you're not going to know about unless you're doing some kind of exploration, unless you're trying things out to see if there's a better way of making decisions. So that's called exploration. So this is often called the exploitation versus exploration dilemma. You're trying to gather information while at the same time trying to maximize your reward. Now, in addition, in the contextual bandits problem, we're trying to use the context as effectively as possible. And when you have context, when you have information, there become many, many more different ways of behaving. Much more complex ways of behaving are possible. And of course, you might not ever see the same context twice. Like you might not ever see exactly the same web user twice, or if you do, it's a very small fraction of the time compared to the vast ocean of users that are out there. So the point is that you can't be learning separately for every context. You need a way of generalizing across contexts. So that's where learning is going to come in, one of the places where learning will come in. Another important issue is selection bias, that we're constantly trying to gather statistics. We're trying to do this exploration, but we're trying to do it while also trying to maximize our reward. So that means the statistics that we're gathering will be very highly biased because they're being collected in this biased way, where we're choosing actions to maximize reward, but that imposes a bias in terms of the data that we're collecting. And then we care about efficiency. We want algorithms that are fast, that we can actually run them, and that don't take up too much memory. Okay, so in this talk, what I want to do is to try to give an overview of some of the algorithms and techniques that have been developed for this problem. So this problem has been, this problem and its variants have been studied for a few decades now. And so I'm going to try to give an overview of a couple of the techniques that have been developed for that. This is, if you look at the newspaper, it seems like all that's happening in machine learning is deep learning, which is certainly not the case. There are actually other important and active areas that seem promising. And so this is an example of that I'm going to try to give you a taste of. Now, what we're looking for is we're looking for algorithms that are general purpose. That's always the style of machine learning. We're looking for methods that are general purpose, that can be used in a lot of different settings, and that will be practical, meaning that they're fast and not too difficult to implement. And in this setting, we're looking for algorithms that will be able to realize complex behaviors. We don't want just simple behaviors. We want, if a complex behavior is called for, we want our algorithm to be able to learn it. And we also want algorithms that will have strong and provable statistical guarantees. So by statistical guarantees, I mean you want to be using the data as effectively as possible so that you're learning as quickly as is possible based on the data that's available. Okay, so that's what we're aiming for. I don't know if it's traditional to ask questions in this setting or not, but if you have questions that, something that I can clarify along the way, do stop me. I realize that I come from a different community, so my language might be different. Okay, so here's a very quick outline. I'll start out by formalizing the learning problem, which actually will take a fair bit of time to really pin down what the problem is we're trying to solve. Then I'll talk about algorithms. And, I'll see if I have time to talk about an application and a next step. Okay, so we'll start by formalizing the problem. So let me start by going back to what I talked about earlier. I talked about this informally already, but let me just go back and add a little bit of mathematical notation. I hope the math won't be overwhelming. You probably could ignore most of the math and still follow the talk, but it's helpful to have some notation for people who care about things being precise. So learning is happening through this series of interactions or rounds, and there are going to be capital T rounds altogether. Is there a way I can point with this? Oh, I can. Okay, does that show up? Yes, okay, so there are capital T rounds altogether. So on each round, little t, what happens? Well, first of all, this agent, the learner, observes some context, like a description of the web user, and we'll call that context xt. Then based on that context, the learner chooses one action that we'll call at. And just to keep things simple, we'll suppose that there are k possible actions, like k news articles that could be presented to this user, and we'll just number them 1 through k. So the user picks one of those actions, or in that example, one news article. And then based on that action, the learner receives some real valued reward for the action that was selected. The reward for the action that was selected. Okay? So like maybe 1 if the person clicks on the article, 0 otherwise. Now, in fact, there's another step that I was hiding here, but where that's useful to think about when we're formalizing this mathematically, which is that before the learner chooses an action, we're imagining that the world or nature decides on what reward would be received for each of the K actions. Okay, so formally that means that nature is deciding ahead of time on a reward vector, which is just a list of numbers, rewards for each one of the K actions, and we're supposing the rewards are between 0 and 1. Okay? And of course, that's not observed to the learner, but then the learner chooses one action and gets to see one of those rewards. All right? And so, whoops, wrong button. And roughly speaking, we're going to refine this later, but roughly speaking, the learner's goal is to maximize the total reward. So this is the total reward received by the learner over all T rounds. Okay, so let me just, for concreteness, oh, one other point, sorry, before I say that, which is we're going to assume for now, I'll change this later, but for now we're going to assume that what happens on each round is random. So there's some unknown fixed probability distribution which is generating these contexts and these reward vectors. Okay, and that from one round to the next, what happens is independent. We're not saying that the context and the rewards are independent of each other. That would say context provides no information about rewards. On the contrary, we're saying exactly the opposite, that they are correlated and context is useful for figuring out which action to take to get high reward. I'm just saying from one round to a next, things are independent. Okay? Okay, so to make this concrete, here's a little tiny toy example. Okay, so in this example, there are 3 actions. And what happens on the first round is some web user shows up, and we have a description of the user. So maybe this web user is a man, and he's 50 years old, and so on. We have a description of him. Then nature decides on what reward would be received for each one of the 3 actions. But of course, that reward is not revealed to the learner. I don't know. Oh, it did show up pretty good on there. And then based on the context, the learner decides on one action. So maybe the learner chooses action 2 and now gets to see that reward of 0.2 in this example and receives that reward. And then we go on to the second round. So now a second user shows up, some rewards are chosen, the learner chooses a new action, maybe action 3 gets a reward, and so on. Okay, and the goal is to maximize this total reward. All right, that's the problem. Okay, so what is the learner really trying to do? The learner is trying to figure out how to choose actions. So that means that the learner is trying to find a rule that will allow it to select actions based on context. So it's trying to find a decision rule for choosing actions based on context. And in this setting, that kind of a rule is called a policy. Apologies for all the other things that the word policy can mean, but here it just means a rule for selecting actions. So just for the sake of concreteness, as an example, this is only an example, maybe the learner comes up with a rule, a policy like this one, which just says that if the current web user is a man, choose action 2. Otherwise, if she's more than 45 years old, choose action 1. Otherwise, choose action 3. Okay? So that's an example of a policy. By no means does it have to have this particular form. In general, a policy is just a mapping. It's just a function that maps contexts to actions. And the learner is trying to come up with a good policy, a good way of choosing actions based on new context, new on each round. Okay, so where do these policies come from? How does the learner decide on where to select these policies from? What kind of policies it can use? Well, as in other machine learning settings, we as the human we as the human need to decide the form of the policies that will get used. So we might decide, oh, maybe we'll use if then else rules like this. This is an example of a decision tree, as I'm sure most of you know. So maybe we'll use decision trees for the policies that this learning algorithm will work with. So as a human, we need to decide on the form of the rules that we're using. Or maybe we'll decide to use neural networks, because after all, that's so trendy now. But in one way or another, the human needs to decide on the form of the policies that will get used. And when we do that, that implicitly defines a space of policies that we're working with, called the policy space, which just means all the policies that have that particular form, like all decision trees in this example. Okay? So we decide on the policies we're going to work with. That defines a policy space. And so what we're doing is we're implicitly making an assumption. Because anytime you use machine learning, no matter what it is, you're making an assumption of some kind or another. Somewhere there's an assumption. And here we're implicitly making an assumption that we believe that there's one policy in this space, in other words, that has that form that we, as the humans, believe will give high reward. Okay? So this is something you have to do when we use this algorithm. So we choose a policy space, just a form for the rules that we're using. And then we believe that there's one good policy, at least one good policy of this form, and our aim now is to try to find that one good policy. Okay. So the goal is to learn by experimenting to do as well or almost as well as that best policy in the space. That's what we're aiming for. That's the learning problem. Now in this talk, to make things simple, we'll assume that this policy space that we're working with is finite, but it will typically be extremely large, like it might be the space of all decision trees, which is a very, very large space, an exponentially large space, but depending on how you set things up, it's still a finite space if you set it up right. So by allowing the policy space to be extremely large, what that really means is we're allowing these policies to be very complex and very expressive in terms of the kind of behaviors that they represent. And so we're hoping that this is going to be a very powerful approach that allows learning algorithms to learn these very complex behaviors. Okay? But there's some big challenges when you're working with this huge space. So like if you're working with the space of all decision trees, this is this exponentially large space. You can't even afford to list all of the decision trees because there are just too many of them. And you can't afford to store all of them either because it's so large. And in this setting, we're trying to be learning about all of these different policies, how well they each perform, while also trying to perform as well as the best one. And when we select an action, we only get to observe the reward for policies that would have chosen that same action. Okay, so we're just getting this limited information about each one of the different policies, about each one of these different behaviors that we're trying to learn about. So in other words, it's the same exploration versus exploitation dilemma, but now on a gigantic scale because we're working on it with this gigantic space of possible ways of behaving. Okay, so probably people are used to thinking more about in terms of models, where you have a model that makes predictions about the data. So this is kind of a different approach where rather than trying to learn a model that tells you, makes predictions about the data, instead it's trying to deliberately prescribe actions. So it's like these policies are taking the place of models in terms of directly telling you how to behave rather than making a prediction about what's going to happen. Okay, so coming back to our formal model, so the first part up here is the same as what I had before, but now I just want to refine what the goal is. So the goal now is that we're trying to get high reward, high total reward, but relative to the best policy in the space. In other words, in comparison to the best policy in the space. So if you have a learning algorithm that performs almost as well as the best policy in your space, then over the long term, eventually you'll be, if there's one policy in the space that's doing very well, then eventually the learning algorithm also will be performing very well. Okay, so to measure that difference in performance, we use something called the regret. Okay, so don't worry too much about the math, but just very briefly, the second term over here, this is just the rewards received by the learning algorithm divided by the number of time steps. So it's the average per time step or per round reward received by the learner. And this is the average reward received by the best policy in this particular space. And the difference between those is the regret. So if the regret is going to zero, then that means the learner's performance is getting very close to the performance of the best policy in the space. All right? And algorithms that have that property where the regret goes to zero are called no-regret learning algorithms. Okay. So that brings me to the end of formalizing what the learning problem is. Maybe I'll just pause, see if there are any questions. Yeah.
I guess just a quick question. If the learner is trying to figure out what's the best policy, that's the objective, how do you know what the best policy? How do you do the max first term?
Well, exactly. I mean, mathematically you can do it, but the learning algorithm can't do it. And nevertheless, what we're aiming for, I mean, you're hitting the crux of the problem. Nevertheless, you want learning algorithms which will provably have the property that they converge to the best performance of the best policy, even though the learning algorithm itself has no way of measuring that. But nevertheless, mathematically, as we'll see, we'll be able to prove that. Yeah. Yeah. Well, that's what we're going to talk about also. Good question. Yeah, how fast does it converge? And that's, when I talk about statistical guarantees, that's what we're talking about. How fast does it converge? And we want fast as possible. So, okay, yeah. Exactly. Yeah, so the learner can't do it, but mathematically, you know, it exists as a mathematical number. But yes, exactly. The learner can't do it. Okay, good. So it seems like people are, all three questions were about the challenges of how we do that. So let me move on and talk about techniques that do that. So we'll start talking about algorithms. I'm actually going to, before getting to the bandit setting, I'm going to talk about an easier setting called the full information setting that we're going to use as kind of a stepping stone to get to the bandit setting. So by the full information setting, I mean the same setting as the bandit setting, except that the learner here can see the rewards for all of the actions, not just for the action that was selected. Okay, so in terms of something like medical treatment, this is a total fantasy. You don't get to find out what would have happened for the other treatments. But nevertheless, as I said, it's a useful stepping stone. So again, going back to this toy example, what happens here is that nature decides on rewards, learner selects an action, but now nature reveals the rewards for all of the actions, not just the action that was selected. Okay? And the process continues, and eventually the learner gets to observe all of this data, the rewards for all of the actions for all of the time steps. Now, why is this a useful setting? Well, first of all, of course, the learner can compute its own total reward. But in addition, what's really nice here is that if we pick any particular policy, we can go back and compute the rewards that would have been received if the learner had always chosen actions according to that policy. Okay, so if we pick one particular policy, we can go back and we can say, well, on this first context, I guess you can't see my finger when I point there. On this first context, This particular policy would have chosen action 3 and gotten a reward of 0.0. On the next round, it would have chosen action 3 again, gotten another reward, and so on. So the learner can go back and compute the rewards that would have been received for any particular policy. And since we can do that for any particular policy, the obvious thing to do is always to choose the policy which has performed the best so far, okay, which has performed best so far. So that particular algorithm is called the follow the leader algorithm. It has a few names, but I'll be calling it the follow the leader algorithm. So again, what happens is on every round, what we do is we start by finding the empirically best policy in the space, the policy in this policy space that performed best so far on the data we observed. That's what I mean by empirically best. And then we just choose the action that would be selected by that policy. Very simple algorithm. It turns out that this algorithm gives the optimal regret. Remember, we want the regret to go to 0. It turns out you can show that the regret of this algorithm is like square root of log of the size of the policy space, okay, divided by t. So since it's logarithmic in the size of the policy space, that means that we can afford to have these gigantic policy spaces that I was talking about. Because it's only logarithmic in the size of the policy space, we can afford to have these really, really big policy spaces. And it's saying that the regret is going to 0 at the rate 1 over root t. And this turns out to be optimal. Okay, so that's nice. So that's what's happening statistically. What about computationally? What if you actually wanted to implement this algorithm? What would be the hard part? The hard part would be this first step where we need to find the empirically best policy in our space. That would be the main computational challenge. So there's really no way around that. One way or another, you need to have your hands on an algorithm or a subroutine that you can use for finding the best policy in your space based on the observed contexts and rewards. Now, coming from computer science, in computer science you would call something like this an oracle. I know oracle has lots of different meanings. I'll call it an oracle, but it's really nothing magical. It's just a subroutine or an algorithm that we can use for solving this problem. Now it might seem like it's solving a funny kind of problem, but if you and it's got different names, this oracle. It might seem like it's solving a funny kind of problem, but if you unravel all the definitions, it turns out that the problem that's being solved up here is just a very standard classification learning problem, just a very standard machine learning problem that's been studied for decades. And all the standard techniques you've heard about, like neural networks and boosting, sport vector machines, decision trees, those are all algorithms for solving this problem, which means we already have a lot of good algorithms sitting around that we can use as oracles for solving this problem. Okay, so I'm not going to say what the oracle is. I'm just going to assume that we have an oracle like this. But what we can really use in practice is one of these standard algorithms like whatever, boosting neural networks. Okay, so I'm going to be talking about various techniques, and I'll highlight them as I go along. So this first technique, we actually talked about a couple. The first is just to estimate the expected reward of each policy. That's what we did earlier. And the second technique is to use an existing method, what I'm calling an oracle, to find the best policy. Okay, so that was a really simple algorithm. Now let's make the problem even harder. So far I assume that the data was stochastic, that it's random, that what happens on every round is random, that nature is random. But that's not always realistic. Like you could have these temporal correlations, you could have data that's drifting, non-stationary, or you could be in an environment that's actually adversarial. I'm sure okay, I won't say it. was going to say in finance, I'm sure there are adversarial settings, but who knows? Not me, all you guys. But certainly in game playing, like actually playing a game, that's a truly adversarial setting. Okay, where the data is not random, you're playing against an opponent. So in fact, we can consider a non-stochastic setting, what's sometimes called an adversarial setting. And in that setting, the contexts and rewards are completely arbitrary. They don't need to be random. They might even be chosen by an adversary, by a bad guy who's deliberately trying to make our performance as bad as possible. Okay, so follow the leader does not work in this setting. You can construct examples that show it doesn't work. Might even seem impossible that in such a difficult setting where there's no randomness. But in fact, there are algorithms that do this. So a classic one is called hedge. It's come to be called hedge, even though it's really based on the weighted majority algorithm of Littlestone and Varmuth. So in this algorithm, just let me briefly at a high level describe the idea of the algorithm. What we do is we maintain one weight, one real number, for every policy in the policy space. So that means maintaining a lot of numbers because you're going to have one for every policy in the space. And then on every round, we basically choose a random policy with probability proportion to the weights. So we kind of take the weights, convert them into a probability distribution by normalizing, and then select one policy at random from that probability distribution. And then we choose an action according to that randomly chosen policy. And then once we get rewards, what we do is we increase the weight of every policy, and we do it kind of in proportion to the reward they would have received. So the higher the reward a particular policy would have received, the more we increase its weight so that next time we'll be more likely to listen to that policy. Okay, so I'm describing it at a high level. Of course, it has a more precise mathematical definition. But if you do it right, you get an algorithm that gives optimal regret, the same regret as follow the leader, but even in the adversarial setting, even when the data is completely arbitrary, which is a really nice property. That's the good news. The bad news is that this algorithm requires maintaining one weight for every policy in your policy space, which means that the time and space requirements will be linear in the size of the policy space. And so if that policy space is gigantic, this algorithm is going to be much too slow. Okay, so nevertheless, I guess I did work boosting into this talk after all. So one place where this algorithm gets used is, in fact, the boosting algorithm AdaBoost actually was derived from hedge. So it's useful anyway, even though it's not for the bandit setting, and despite this limitation. Okay, so here we have another technique, which is to use a weighted combination over the policies, a weighted combination of policies, rather than just one. Okay, I'll skip proofs. So just to summarize this part of the talk, I talked about two algorithms for the full information setting. Follow the leader and hedge. Follow the leader is for the stochastic setting, hedge is for non-stochastic setting. They both give optimal regret. Follow the leader is efficient if we have an oracle, if we have this oracle, this subroutine for solving that main computational problem. Hedge is inefficient if the policy space is gigantic. Okay, so let me move on to the bandit setting since time is short. Okay, so let me come back now to the bandit setting. And again, in the bandit setting, we only get to see rewards for the actions that were taken. So coming back to this example, rather than seeing rewards for all actions, we only see rewards, or the learner only sees rewards for the actions that were actually taken. So where did the ideas that we talked about before go wrong? Why don't they work in this setting? So the learner can still compute its own total reward because it can see the rewards for all of the actions for the action that's selected. So what if we try to do what we did before? So we pick a particular policy and we try to figure out what reward would have been received for that policy. Well, we still can go back and compute which action would be selected on each one of the contexts. But for instance, on this first round, the learner selected action 2, and this particular policy would have chosen action 3. And since the policy chose a different action than the learner, we don't know what reward would have been received if we had listened to that particular policy. Okay, so we don't know what reward would have been received on the first round. On the second round, we do, because it happens they would have picked the same actions. So in general, the learner can only compute the reward that would have been received on a subset of the rounds, namely on exactly the rounds where that policy would have chosen the same action as the learner. Okay, so we might still want to use this oracle, but the problem is we only get to see some of the rewards, and also the rewards we do get to see are very highly biased. This is that selection bias, that problem that I mentioned before, that we're collecting data in this very biased way, so the rewards we do see will be biased, skewed. Okay, so maybe I'll skip this since I'm a little bit short on time. So I think it should be clear that we need to be doing some kind of exploration. I already mentioned that, how it's important to be trying new things out all the time. And follow the leader will not work. The follow the leader algorithm will not work because what can happen is it can kind of get stuck doing the wrong thing. Nevertheless, we can take the follow the leader algorithm and we can modify it by kind of forcing it to do some amount of exploration. So this leads to a technique that's called epsilon greedy, or a more refined version is called epoch greedy. So the idea is really simple. So on every round, what this algorithm does is it chooses the action in one of two ways. So with probability 1 minus epsilon, let's say 95% probability if epsilon is 5%. So with 95% probability, we'll just do what follow the leader does. We'll just choose the best policy so far. Otherwise, with 5% probability, we'll choose one of the actions uniformly at random. Okay, so we're just kind of doing explicit exploitation for the first part or explicit exploration for the second part. And by the way, this part of finding the best policy so far, it turns out you can do that using the oracle. Okay? So this is called epsilon greedy. Like I said, it's a very simple and fast algorithm if we have an oracle. That's the good news. The bad news is that this algorithm does not give optimal regret. So the regret that you can get is like k number of actions times log size of the policy space divided by t. So this inner part is the wrong thing, but is the right thing. But then for this algorithm, it turns out that the regret is cube root. So that to the 1/3 power. And it turns out that the optimal regret would have a square root, would be that to the 1/2 power. Now you might say, what's the big deal? 1/2, 1/3, you know, is it a third of a pound hamburger, a half pound hamburger? Who really cares? But this difference between 1/2 and 1/3, that's actually turns out to be a big difference. It means a big difference in terms of how much data you need to get equivalent performance. Okay, so the technique here is to use this explicit trade-off between exploration, or this explicit exploration using uniform sampling of actions. Okay. Okay, so I talked a lot about selection bias, and selection bias is a major problem, but it turns out there's this really simple trick for dealing with selection bias, which is called inverse propensity weighting. So the idea is that suppose you want to estimate the expected value of a random variable x, you just want to know what its expected value is, like the probability of an unfair coin coming up heads. And To make it harder, suppose with probability p you get to observe this random variable once, like you get to flip the coin once and see its outcome. But with probability 1 minus p, you don't even get to observe it once. You don't even get to observe the coin at all. And yet you want to end up with an unbiased estimate. How do you do that? Well, there's this little trick, which is you form a new random variable called x hat. And what happens is if you're in the case where you actually got to see the random variable, so you got to see this coin being flipped, you take the outcome, x, and divide by p, the probability of observing it. And otherwise, you just let this random variable be equal to 0. It's called inverse propensity weighting. What's nice is that even though x is only observed some of the time, just like the rewards for the different actions, this new random variable x hat is always observable, and it turns out that it has the right expected value. Its expected value is the same as the expected value of x. So if we just take this outcome of x hat, it's an unbiased estimate of x. And we can use that same idea to estimate, to get unbiased estimates of the rewards for all of the actions. This is called inverse propensity weighting. So we can get these unbiased estimates. Does that mean we're done? Well, no. They have the right expected value, but their variance can be gigantic. So even though I was saying selection bias is a big problem, that was kind of a lie. The real problem is that the variance of our estimates can be gigantic. That's the real problem. So really what we need to do is control variance, which can be done using various techniques, such as uniformly sampling actions. So this is another technique in our list of techniques, which is to use inverse propensity weighting to get unbiased estimates. Okay, so let me come back to this non-stochastic setting. So now we're probably at the hardest setting of this entire talk because we have bandit feedback, so just very limited feedback. And it's in this non-stochastic setting where you don't even get to, where an adversary is controlling what's going on. So even in that very difficult setting, it turns out that there's an algorithm called XP4 that can solve this problem in the non-stochastic setting. And it's combining hedge with uniform sampling of actions and inverse propensity weighting. And if you do everything right, you can get optimal regret for this setting, where that 1/3 becomes a square root. But well, let me skip that. But like hedge, its time and space requirements are linear in the size of the policy space, so it's going to be much too slow. Okay, so let me summarize where we are and where we are. So far for the bandit setting, we talked about epoch greedy for the stochastic setting, which gives regret, which is like 1 over cube root of t. And we talked about XP4 for the non-stochastic setting, which gives the optimal rate, which is like 1 over square root of t. And again, this 1/2, 1/3 might sound small, but it's actually a big difference because it's saying to get a regret of epsilon, you need 1 over epsilon cubed trials or rounds for epoch greedy, and only 1 over epsilon squared rounds for XP4. So that's like a big difference between cube and square when you're talking about large numbers. So you might ask, is it possible to do both? In the stochastic setting, can we get an algorithm that gets optimal regret? And so that brings me to the last algorithm that I wanted to talk about. This last algorithm is the most recent of the algorithms that I'm talking about. So this algorithm, it mainly goes by its nickname, which is the mini monster algorithm. It has an equally obscure real name, which is I love toucan bandits, which even though I'm an author, I can't remember what that name means. But it doesn't matter because everybody calls it the mini monster algorithm. I'll explain why it's called that in a minute. So basically, the idea is to take all of the techniques that I've talked about today and combine them, and to add one more technique So you remember with hedge, one of the techniques that we talked about is to find this weighted combination of policies. So now what we can do is we can, instead of finding this weighted combination the way hedge does it, we can try to find a weighted combination over the policies that will satisfy exactly the properties that we're looking for. We can explicitly write down what properties we want that weighted combination to have. So there are only two properties. The first one is we want it to give low regret based on our current estimates. So in other words, the obvious thing, we want to choose actions that we think will give high reward. And the other thing is that we want to make sure that we're getting good statistical estimates. So we want the variance of the estimators we're collecting to be low so that our future estimates will be accurate so that in the future we'll get low regret. So these correspond exactly to exploitation and exploration. And you can formulate these, you can write them down mathematically, you end up with this gigantic optimization problem. It's huge and complex and ugly and awful. And it turns out that despite that hugeness and ugliness, there's this very simple and efficient algorithm using this oracle that I talked about earlier, which can solve that problem. I'm not going to describe the algorithm, but there's this very simple and efficient algorithm for doing this that solves this optimization problem so that you can end up with a weighted combination of policies, and then you just select one at random according to that weighted combination. So this algorithm gives almost optimal regret. It's also a very fast algorithm, so you can measure speed by how often you have to call the oracle. This algorithm, it turns out it only has to call the oracle about once every square root of t rounds, so very infrequently, which are nice properties. It's based on a previous algorithm, which was officially called randomized UCB, but this was such a complex and awful algorithm that even the authors of the algorithm themselves called it the monster algorithm. So that's how this new algorithm came to be called the mini monster algorithm. Okay, so this is the last technique, which is to formalize what we're looking for, the properties we're looking for as an optimization problem, and then solve it. All right, so I'm pretty much out of time. So let me just very quickly mention, I feel like I should mention one practical use of this. So I'm not involved in this, but other people in my group and at Microsoft have developed a system, a computer system that implements contextual bandits, and it's a really nice system, and I'm not sure the level of, I think it's available publicly now. It's very general purpose, modular. You can use it. It's set up so that it's easily interfaces with other existing systems. It's really a nice piece of software. So as one example of where it's used, it was deployed on to actually select news articles on the MSN homepage. And this is an example where MSN apparently had used many other learning techniques to try to solve this, and none of them had worked. And using this so-called decision service, they were able to get a 25% improvement in click-through rate, which is really a big deal. And so it's used now on the MSN homepage. Okay, so let me skip this, and I'll just conclude. So again, this contextual bandits problem, it's really a very challenging problem, and I talked about some of the things we're looking for. We want an algorithm that's computationally efficient. We want to be able to work with these large policy spaces, which is equivalent to saying that we want to be able to learn really complex behaviors. We're looking for optimal statistical performance, which means you want the regret to go to zero as quickly as possible, so you're using the data as efficiently as possible. And sometimes you also want algorithms that work in the adversarial setting. So there's been a lot of work over the last couple of decades building up these methods that I tried to overview. And one lesson of this, which is very typical of machine learning, is that theory has really been very helpful, really not just helpful, but really indispensable, something we really needed, and then slowly starting to pay off in practice as well. So I think the slides are available online, and on the last slide I also have a list of references. So that's it. Thanks.
We have time maybe for a couple of questions, but again, you can continue the conversation.
Yeah.
So in context of, I think reinforcement learning is in a lot of vogue now. So is the difference between what you presented today in terms of contextual bandits and reinforcement learning more the impact on the environment by the actions which are taken? And specifically in the context of finance, do you think, bandits would be more useful if the impact on environment is not that high?
Well, so the question was about the connection to reinforcement learning. So on the one hand, bandits is kind of a special case of reinforcement learning, depending on how you set things up and how you think about things. There are a few differences. So one thing is that we're thinking about there being this context, and we're thinking of the context as being something really rich, like the description of a patient, which might have documents and, in other settings, maybe images and so on. So we're thinking of the context as being something really rich, which is not so typically done in reinforcement learning. But another difference, which is really important, is that in reinforcement learning, there's a notion of underlying state. So like in that medical example, the patient has an underlying condition which is changing over time. I set it up that this patient comes in once, the doctor does a treatment, and that's the end of it. But of course, in real life, the patient comes back over time, and their treatments, and this underlying condition, this underlying state is changing over time, which is really the fundamental thing that reinforcement learning is trying to get at. This work has ignored that, so we're not paying attention to underlying state, but we've been doing more recent work. That was one of the things, that was this next step slide, which was more recent work where we're trying to pull together contextual bandits with reinforcement learning, where you have a model with some kind of underlying state that's changing, and you have these rich contexts. And we've made some progress on that, so we've come up with the efficient exploration algorithms, but it's a much harder problem to try to prove things in.